All right, welcome back. I hope you're having an amazing time so far. Our next speaker is Bahman Rashidi. He is the Senior Security Architect at Comcast Cable. Please join me in welcoming Bahman to our virtual stage.
Hi, everyone. I'm Bahman Rashidi, and I'm a Senior Cybersecurity Researcher and Architect at Comcast Cybersecurity R&D team. And what I'm going to present to you today is XGITGuard. XGITGuard is an AI-based tool which is developed fully in-house at Comcast Cybersecurity R&D team. And what it does, it helps us to detect organizational secrets that have been exposed or leaked publicly. And to be specific, we're talking about GitHub. It does it at scale, it's agile, and it does it in an accurate way. These type of secrets that have been leaked, either we're talking about secrets that have been leaked accidentally, or sometimes it's a result of some misconfigurations by developers that these secrets end up being exposed on public GitHub. So as you know, on GitHub, users have two options to share their code. One is privately, that they can make their repos private, and one is public. And sharing your code publicly, that's where the risk is. So we're trying to, what we're trying to, by finding these secrets that are being exposed, is to avoid data breaches at organizations. And avoid something that happened to Uber in 2014, that 50,000 records were breached, and that was the result of a secret that was accidentally posted on public GitHub, and that attack was successful because of a secret that was leaked on public GitHub. So XGITGuard, what I'm going to present to you is a successful application of AI in cybersecurity. XGITGuard uses machine learning algorithms and text processing algorithms that we have developed ourselves, and it will help us to find these secrets accurately in an agile way in a very short period of time, from the time that this secret has been exposed publicly to the time that we detect it. So once we have all this detection from XGITGuard, there is an extra layer or extra level of validation. The secrets that we find will go through a machine learning model that does the validation part and make sure that the secrets that we're finding are true positives and they're not false positives. So this will help us to have a higher accuracy compared to other tools in the area. So secrets. What do we mean by secrets? When we're talking about secrets in this, in XGITGuard, we're talking about credentials and tokens and keys. So we're separating these two types of secrets because the way that we approach finding and detecting these secrets on public GitHub are different. So when we're talking about credentials, we're specifically talking about username, passwords, clear text passwords, server credentials, account credentials that are basically clear text secrets. And then we are also talking about token and keys. Specifically, we're talking about service API tokens and examples of like AWS, Microsoft Azure tokens, encryption keys, and other similar tokens. So we will have two different approaches for these two types of secrets. They're slightly different. We'll get into details that how our approach is different when it comes to these two types of secrets. I'd like to give an overview of how XGITGuard works before I jump into the internal components and architecture of XGITGuard. So the way XGITGuard workflow is, we will start by searching GitHub at scale. And this is where we will use the GitHub API, search API, to search for repos and code, specifically for the repos that are publicly available. Then the results will be filtered. Whatever comes back as a result of these APIs, we will filter them to remove the noise. Such as, for example, if sometimes a file has no content, or it has a little content, which is really not what we're targeting, So once we remove some of the noisy files and noisy data, these files, which are candidates, will be passed to our core engine, which is, it will help us to detect the secrets, extract the secrets, creates the context around that secrets, that where the secret is within that repo, which line of code, and so on. So once that happens, then we have the developer identification part, and that's where XGITGuard will look into the historical commits and find out like which developer was the one who posted that secret, or which user was the one who posted that secret on that repo. So we will get the contact information for that user, and then, as I said, it will go through the validation process, and this is where we validate that secret. We will come up with a confidence score for our detection, and the results will be will be submitted to a dashboard. So, for example, here it can be swap. So, as I mentioned in the previous slides, there are two types of secrets, and we treat them differently. Just because of the nature of these secrets, we should have different approaches in detecting them. So for some parts, they are kind of similar. However, there are differences. For example, when it comes to finding passwords, it's a bit more complex than finding tokens and API keys. And the reason for that is that mostly passwords and other similar credentials like password don't have a specific patterns. They don't follow specific rules. I mean, there are rules for creating a password in some systems. However, what makes it hard is that every system, every organization, they have different rules, different policies. Sometimes they are very well-known policies, and sometimes they are very customized to your organization. And that makes it a little bit hard compared to things, let's say, for example, AWS tokens, that they have specific patterns, and regexes that are out there. So that's why we have a different solution for credentials or passwords, and one for API tokens. What you're seeing here is the core architecture of XGITGuard for credential detection. What you're seeing here is that basically 5 components. It starts from searching GitHub and all the way through the validation phase. So the first element here is that where we are crafting the API, crafting the queries using GitHub API. So XGITGuard uses the latest version of GitHub API. And in order to issue those queries, we need keywords. We need these keywords to craft our queries before and submit them to GitHub, so we can receive some results and some repos and candidate files as the files that we need to review. So we have our approach is that we have 3 types of keywords in order to craft these queries. The first one is the primary keyword. The purpose of this primary keyword is to help us narrow down our search or to documents or repos that potentially have some kind of a relation to our organization. For example, in here, I'm using abc.xyz test. This is, for example, a keyword that is relevant to our organization. And the organization is, let's say, xyz test. So we are looking for documents that contain this contain this keyword. We can have a long list of these keywords, go through the organizational documents and the tokens or the keywords that are related to your organization. You can put them in the primary key. So, and then the next thing is the secondary keyword. The purpose of secondary keyword is that once we do the primary, once we narrow down to the documents that are potentially relevant to your organization, it comes down to when we need to narrow down those findings or documents to the ones that potentially contain some kind of a secret. So that's where we make sure that in our query that we are sending to GitHub, we make sure that documents should contain some kind one of these secondary keywords. And here, for example, we have password, we have secret, and so on. So then the next part is extension. As you know, the way GitHub API works is that once you issue a query to GitHub, GitHub will send you a list of findings relevant to your query. Sometimes you can tune it and configure it to the latest documents or the most updated documents, or and so that's when there is no specific extension. So for example, once you issue the query, all kind of extensions can come to you as a result of that query. So what we do here, we want to specifically mention that what kind of extensions we are looking for. And this will help us to cover all types of files, because as you know, the secrets and credentials could be maintained in different types of files. So that's why we use these extensions. So we have, for example, JSON, config file, Python file, and a long list of these extensions that potentially or historically have been used to maintain secrets. So once we have all these primary, the search keywords, which is one of the main parts of XGITGuard, this will be passed to the query engine. So the query engine will help us to boost our search by taking advantage of the multiprocessing. And this is where the inputs will be, the input will be the search keyword, and then it will craft these queries by the keywords. For example, it will grab the abc.xyz test.test plus password plus JSON. This will be one of the queries that will be used. So depending how many keywords we have, the total number of queries that will generate is the Cartesian product of all these keywords. So once all these keywords or the queries have been crafted, they will be issued by XGITGuard in a way that we're not violating the GitHub API limits, query limits. So once these queries have been issued, the results come back. The first thing that we do before we process those files for secrets is that we will calculate a hash of all the results, a hash of the URL of the file. So we do that for this purpose, that so once we process the file, we don't want to process that same file one more time. So the reason we calculate this hash is that we will check within our hash list in our hash table whether there is a hash of this URL in the past that has been processed. So that means this file has been processed by XGITGuard in the past, so we don't process it twice. So once the hashes are calculated, and we find out that there is a new list of files that haven't been processed in the past by XGITGuard, that will be passed to the text processing, which is basically the core part of XGITGuard, or the core element of XGITGuard. And this is where the secrets will be detected and extracted. So the text processing part starts by breaking down the documents into course tokens. And this is, for example, an example of it could be a line of code in a file that could be one token or one course token. So once we do that, then we do the denoising, and this is where we will remove some of the details, some of the comments within the code. We make sure that we're only targeting the lines that potentially contain some secrets. So once we do remove the noise, then it comes to fine tokenizing. This is where we will break down the course tokens into words, into shorter length strings. And then that will go through our stop word reductions. And this is where we will make sure that we are removing the words or the tokens that are just basically a stop word. So for that purpose, we use the English stop words reduction, which is pretty common, and the programming stop words. This is something that we have created ourselves. It's a database of common words across all a number of programming languages, the most common programming languages. So these words will be reducted from the documents, and then the documents will go through our algorithms, which it does the extracting the secrets. And this is where the text, the words will be processed to see which ones look like a password using our text processing algorithm. And then when that happens, the secrets will be detected basically. And this is where, now that we have the secrets, we will create a context around that secret. And the secret, I'm sorry, and the context is something like which line of code, apologies, which line of code this secret was into, right? And that helps, specifically helps the CSOC teams when they are trying to remediate and take action on these detections, that they can easily find where the secret was, and they don't have to go through or find or search through the documents to find the token. So that will happen, and then we will calculate a risk, a score or a confidence score based on a number of factors that we have. We calculate a number of factors, and then out of those, we will calculate the final confidence score. Some of those factors could be, for example, the entropy of that, the entropy of the data, how similar that token looks like to English dictionary words, how similar it looks like to non-English dictionary words, how similar it looks like to true positive secrets that we have found in the past, and so on. So those a number of factors will help us to calculate this confidence score. And then finally is the validation phase. This is where our machine learning tool comes in, and it validates these secrets. The machine learning model is trained based on the past true positive and false positives. And that way we make sure that this secret is potentially a secret with a high confidence level. So once these secrets are validated, the ones that are flagged as true positive will be sent to a dashboard. So that dashboard could be any platform that the organization is using. Could be Splunk, it could be other, it could be, for example, AWS QuickSight or any other dashboard. So this is basically credential detection, how we do the credentials. And as I said, there is a similar but different approach for token detection, token and key detection. It's mainly similar in terms of the query engine and calculating the hash and validation phase. The difference is that the search keywords. So for tokens and keys, we are mainly relying on regexes and pattern. So that means that regardless whether a document contains a token or a secondary keyword as password or key or token or something like that, it does not matter. So because we are relying on regex, so the whole document will be broken down to finer tokens and will pass to the model. So so we have the search keywords. We don't have the secondary keywords for the reason I mentioned. We only have the primary and the token and then the extensions. This will be passed to the query engine, passed to the calculating the hash for those detections, and then it'll be passed to the text processing. And similar process, it will be broken down to the lines of code, remove the noise, remove the stop words, and then the regex checks will happen on those tokens. And whatever we find, most probably with a higher confidence level than credential detection, will be passed to the dashboard. And similarly, we have a validation phase that, again, we use a machine learning model, which is trained by historical detections. And that will help us to validate our detections. Even though we're using regexes, which most probably they're more accurate, but still we pass them through this validation phase, the validation model. One thing I want to mention is that the quality of validation depends on how you train your model, and how accurate and comprehensive is your training data. So with our implementation, we have an accuracy of about 90% of the time correct, in terms of detecting the actual secrets. Um, so this is just an example of how these detections can be dashboarded. This is an example of using QuickSight for dashboarding the detections. As you can see on this dashboard, it shows you the total number of detections coming from keys or coming from credentials. It shows you the top 10 offenders or developers who have posted secrets on public GitHub. And then it shows the most common keywords that have been used to find and detect the secrets. For example, the secondary keywords or extensions, um, uh, or primary keywords. These are the top ones that have been used to identify these secrets. And another piece is basically a timeline of detections, how many detections we have found in the past by the timeline. And this is how it looks like. This is just one sample of a detection. As you can see, we have a timestamp that this was detected, the primary key that was used, secondary key, extension, URL to the specific file that was found. I mean, we're using generic keywords here, but it will show you where exactly that file is, the user or the owner of that repo, the repo name, the credential itself. This can be masked for security purposes by your organization. And then the code itself, the line of code that the secrets was detected. I would like to present and show a demo of how XGITGuard works, the main functionalities of it. One point that I would like to mention here is that we are in the process of open sourcing XGITGuard. So as soon as we decide to release it, it will be on the Comcast open source GitHub. The entire code can be shared there, and you can use it for your organization. And the only thing, the one thing that could be, one thing that is the input to XGITGuard is basically the primary keywords, the secondary keywords, and the extensions. These would be the inputs to XGITGuard, and that is depends on your organization or depending on your use case. Those keywords could be different. So those could be customized or very specific to your organization that will be used as the input to XGITGuard, and then it will identify the secrets. So I'm gonna do a quick demo of XGITGuard and how it works. And this is a pre-recorded video, files and documents that you would like to monitor. So these secrets, these keywords that you see here, these are extracted from this repo. This is a sample repo that I've created just for this demo, for the demo purposes. And we have two files here. The first one is basically a simple login, and there is the keyword XGITGuard demo 2020, and I have that as a primary keyword. For example, I like to process files on public GitHub that contain this keyword, and then basically password as a secondary keyword. The second file that we have is token based authentication, and I'm using a domain. This is just a sample domain, just for the demo purposes, and I put that in my primary keyword as well, and then the API token keyword as my secondary keyword. So so we have everything here. And before I run XGITGuard for these keywords, as soon as I run XGITGuard, it will show us, XGITGuard will create combinations of these keywords, right? And then after it creates those combinations of keywords, it will craft the queries and then basically run those queries.
And what we will see as the output is basically the total number of combinations of these keywords, which is basically the total number of, right? And then after it creates those combinations of keywords, it will craft the queries and then basically run those queries. And what we will see as the output is basically the total number of combinations of these queries and then how many have been processed, whether there was a secret or not. And one means that yes, there was a secret. And then so on for other combinations of these keywords. And then you see there is another combination, which is this one had another secret. And as I said before, we calculate the hash for all these queries so we don't process the files again. And that's why you can see here we had a detection for this combination, but the second time it says 0 and there was no detection. And that means basically we didn't process that file for the second time. So I'm gonna stop XGITGuard and then look at here. This is basically when we run XGITGuard, it will create a file for us where it keeps all the secrets that have been detected. So I'm gonna open it to see how many secrets we have found.
So as you can see, there these are the secrets that we had in our repo and in our files and have been detected. And based on the sample that I showed, the username, URL to it, the code itself, the line of code, and so on. So thank you very much for attending my talk.
Wow, thank you. That was amazing. And I know this virtual audience is giving you a huge virtual round of applause. That was awesome. And we really appreciate you sharing with us today. For
Thank
the
you very
audience,
much.
yes, thank you. For the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.